Hello students, this is Mr. Ezra. We are going to start our notes on Chapter 9 today since I'm stuck at home with a sick kid. I thought I would record this video for you and let you go ahead and start the notes and get started on some practice. So after you finish this video and you get the notes, this is the section that you should start working on. This is kind of like your first homework assignment for this chapter. Just the part for 9.1 of stating correct hypotheses, interpreting p-values, reading and kind of adding to your notes from these pages, and then working on 1 through 13 odd on page 546. So we introduced in a very kind of basic way significance tests in class on Friday, and now we're going to start our notes. So there are really two formal types of inference that we use in this class. One is a confidence interval. We've talked about confidence intervals already. They are used to estimate a population parameter. So we don't know what mu is. We use a confidence interval to try to estimate what mu is. We don't know what the population proportion is. We try to use a confidence interval to estimate what that is. The second type of inference, and what Chapter 9 introduces, is something called a significance test, also sometimes called a hypothesis test. These are used to assess evidence for a claim about a population. And both types of inference are based on sampling distributions, which we studied in Chapter 7, so we're still going to be using that idea of a sampling distribution. So we've got a few questions here where we just want to decide, is this a confidence interval or a hypothesis test? Should we do a significance test or a confidence interval? Number one, you measured the heights of a random sample of 400 high school sophomore males. The sample mean is 66.2 inches. Suppose that the heights of all high school student sophomore males follow a normal distribution with an unknown mean and standard deviation. You desire to estimate the mean height for all high school sophomores. Well, I think that you can see we are trying to estimate the true mean height for all high school sophomore males. That is going to be a confidence interval. That's what we would use here. Number two, a researcher wishes to determine if students are able to complete a certain pencil and paper maze more quickly while listening to classical music. Well, so they're going to have a time for completing the maze without the classical music, and now we're trying to see whether classical music will improve the time. So we're testing this claim that classical music is going to help the students on the paper and pencil test. So this is actually going to be a significance test, or a or a hypothesis test. Finally, an engineer designs an improved light bulb. The previous design had an average lifetime of 1,200 hours. The mean lifetime of a random sample of 2,000 of the new bulbs is found to be 1,251 hours. Although the difference is small, he would like to know the difference if the difference is statistically significant. So we know it's true of the population of light bulbs. We've got a new design. We believe that it may be improved, might have a longer lifespan. So we are testing a claim about a population. That's going to be a significance test, or it could be called a hypothesis test. So I guess especially on the AP test, when you're not going to be given what you're supposed to do, the first step with these questions, you have to do some inferences. What kind of inference am I going to do? Is it a hypothesis test or a confidence interval? And it's going to be easier for you the more of each type that you see. It's not going to be difficult. You're going to see it and go, oh, this is what they want me to do here. So remember with confidence intervals that we get this interval that we have some confidence we've captured the true population parameter of interest, but we might not actually capture it. The same thing happens with significance tests. We believe that we have the right decision, but sometimes we make the wrong one, and we're going to talk more about that later in this chapter. Let's make the claim that the true proportion of Cairo High School students who do not drink alcohol is 0.62. That's the claim that's out there. Now, you might think that that's an overestimate. The proportion is actually less than that. So your claim is going to be that it is the proportion of Cairo High School students who do not drink alcohol is less than 0.62. So we take a simple random sample of 100 of these students and we ask them if they've drunk alcohol in the past 30 days. And from this sample, we get a sample result, a sample proportion of 58% from this survey. Now, one of two things is going to happen here. Either the initial claim was true. 0.62 is the true proportion of Cairo High School students that do not drink alcohol. But you know, when we sample, there's variability in sampling. It happens naturally, and we just happen to get a sample proportion of 0.58 because of that sampling variability. Or it is also possible that the initial claim was false. So this sample proportion was not unlikely to happen, thus proving our belief, in fact, that the true proportion is less than 0.62. 0.58 is so low that we feel like we have evidence that the initial claim was wrong. So either the initial claim is true or the initial claim is false. One of those two things is happening, and our job is to try to make the best decision that we can based on our statistical evidence. So how do we do all this? Well, first, we need to write our claims and the beliefs about our claims in a more statistical manner. Okay, the initial claim that we want to prove wrong is called the null hypothesis. It is shorthanded with a capital H and a little sub O, the null hypothesis. The null hypothesis, please remember this, will always use an equal sign. So the original claim about the population that we're testing that we believe may be false always has an equal sign. The belief that we want to prove right is the alternate hypothesis, and that is a capital H and a little a. And sometimes I have this bad habit of calling the alternative hypothesis, which probably is fine. I don't think anyone would take off points, but it is the alternate hypothesis. Now, the alternate hypothesis will always use one of three inequalities. It's either going to be less than, greater than, or not equal to. The null hypothesis and the alternate hypothesis are mutually exclusive. There cannot be any overlap. So you can't have less than or equal to, greater than or equal to. It has to be less than, greater than, not equal to. Things that are never going to also be equal. Okay? If you use the less than sign or greater than sign in your hypothesis, if it's less than or greater than, that's called a one-sided test. And we'll talk a lot more about that later, but maybe if you think about a sampling distribution and you think about less than as just being one side of that distribution, maybe that's why a good visual for you to think of why it's called a one-sided test or a one-tailed test. If you use the not equal to, you're not making a distinction of less than or greater than. So you are really looking at both sides, less than or greater than. So it's called a two-sided or two-tailed test. Very important that you remember this. So are you paying attention? Get in my camera here. Are you looking into my eyes? Okay. The hypotheses always refer to the population, never the sample. You must use population symbols in your hypothesis. You must use language about the population in your hypothesis. If you reference the sample, it'll be a mistake, and you'll be penalized for that mistake. Okay, we're talking about something that's true for the population. So in addition to writing the two hypotheses, we need to also define this parameter for the population. All right, now there's two ways that you can do this. Okay, one way that you can do this is you can, next to your null hypothesis, let's say in the Cairo High School we said that P was equal to 0.62. And then right next door to that, we could say that that is the proportion of all Cairo High School students who do not drink alcohol is equal to 0.62. So you can either write it in symbols or text. And the alternative we said was that it was less than 0.62. And again, you can write it in symbols or text. The proportion of all Care high school students who do not drink alcohol is less than 0.62. But that's a lot of writing, right? I think what most of you guys are going to do is not necessarily write this next to each of these proportions, but just write your hypotheses in symbol notation. And then below it somewhere, define P. P is equal to the true proportion of all Care high school students who do not drink alcohol. We must define our parameter so that we know what this letter stands for. We know what we're trying to test a claim about. All right, so here is an example. Before I start this example, in our course, we really are going to be concerned about inference for means and proportions, and then we'll move on to chi-square and something else a little bit later on. But other statistics and other parameters we're really not going to be concerned with in formally working through this procedure. But in this example, we are going to be using standard deviation. So don't let that throw you. That's not going to be a normal thing, but certainly we could do this procedure about other things than means and proportions. Okay, that's just kind of what we're going to focus on in this course. So example, Zach Holland is an avid golfer who'd like to improve his play. A friend suggests getting a new club or new clubs and lets Zach try out his 7-iron. Based on years of experience, Zach has established the mean distance that balls travel when hit with his old 7-iron, which I think, this is what throws me out of this problem, because it's not a real world problem, it's a made up problem, because what golfer is going to keep these kind of records on exactly how far he's been able to hit the golf ball? But let's pretend that he has done this, and he knows that with his old 7-iron, his mean, and this is a population mean, remember this, mu is population, with the old iron is 175 yards with a standard deviation of, that's population standard deviation of 15 yards. Now he's hoping that his new club will make the shots with a 7-iron more consistent, because in golf, consistency is important. You want to be able to control how far you hit the ball, and you want it to be consistent. So he goes to the driving range, hits 50 shots, so he's got a sample size of 50 with the new 7-iron. The parameter that he's interested in this setting is the standard deviation. So he is the claim about the old club was that the standard deviation was 15 yards. He wants to know if the new club is different, is better, is more consistent. Okay, so the parameter of interest is the standard deviation length of all shots, right? That's describing the population with the new 7-iron. That's where his sample is drawn from, is the new 7-iron. He's only using the new 7-iron here. So the standard deviation length of all shots with the new 7-iron. The hypotheses for this, we can write, once we have defined the parameter of interest, we can write it very simply. The null hypothesis is going to be simply that the true standard deviation is going to be the same as it was for the old one, and it's not going to change. It's still equal to 15 yards. The alternate hypothesis, though, he thinks it's more consistent with the new, he hopes that it's going to be more consistent with the new 7-iron. He hopes that the standard deviation is going to be less than 15, that it's less variable when he hits this ball. So we've been talking about how to write a hypothesis, and now we're going to move to another part of this process, which is interpreting p-values and statistical significance. So I want you to think about our judicial system. Arrested people are considered innocent until they're proven guilty. So we could say that the null hypothesis is that the defendant is innocent, and the alternative hypothesis is that the defendant is guilty. Now, prosecutors have to provide enough evidence against the defendant's innocence to the jury for them to reject the null hypothesis in favor of the alternative hypothesis that the defendant's guilty of the crime. Do juries ever make the wrong decision? Do they ever put people in jail who were innocent, or let people go who committed a crime? Well, of course they do, right? So there are two types of mistakes that the juries could make, and we're going to talk about that a little bit later in this chapter. But for now, let's just kind of think about what this means in the context of the types of problems we're going to be looking at. For a jury to decide that the defendant is guilty, there needs to be a certain level of evidence for them to make that conclusion. It's not enough evidence if not enough evidence is provided to prove guilt, then the jury will fail to reject the defendant's innocence. This is a really important concept, right? The jury does not prove the defendant is innocent. You know, their job is either to, based on the evidence, conclude that he was guilty or not guilty. And with interpreting these types of problems, you're going to see that that analogy works perfectly because we are going to be looking at statistical evidence. And what we want to know, is there statistical evidence to reject the null hypothesis? Or do we not have enough evidence to reject the null hypothesis? Now, the amount of evidence that's needed to change the jury's mind from innocent, which would be failing to reject the null, to guilty, which would be rejecting him, is referred to as a significance level. And there is a symbol that we use called alpha. Okay, just a little right. Alpha, another Greek letter, right? So the sig level, significance level, or alpha level, is the amount of evidence needed. Now, this value is tied to that idea of a confidence level that we talked about for confidence intervals in our last chapter. A 95% confidence interval would have a 5% alpha level. A 99% confident would have a 1% alpha level. I think that you can see the kind of interplay there between them. You can set your alpha level anywhere you want, to be honest. Very common alpha levels are 1%, 5%, 10%, but the most common that we see more than any other. It's used in, scientific journals. If you want to get published, 5% is usually a good alpha level. So unless a question tells you to use 1% or 10% or something like that, you want to use 5%. That's generally what we would use. Okay. Now, when we set our significance level, when we decide what's going to be our cutoff for proving guilty or for rejecting the null hypothesis, we really want to set this before we perform the significance test. Otherwise, it's kind of cheating. So, like if you get a p-value and then you look at your p-value and you go, oh, well, in order to have significance, this is the alpha level I need. Well, that would be cheating. It'd be like you're a pole vaulter and you know how high you can jump already, so you set the bar low enough so you'll always jump over it. If you set the bar first and you know how high you can jump, then you may or may not clear the jump. So the last scenario is what we want to do. We want to be fair. We don't want to cheat. We have to set our alpha level and then work through the problem. So our alpha level is set. Let's say it's 5%, right? The total evidence provided to the jury can be thought of as the p-value. Now, p-value is really going to be, we'll find out, is a probability. Okay, it is the probability computed, assuming that the null hypothesis is true, that the statistic would take as extreme a value as what the sample gave, or something more extreme. So if the p-value, or this evidence, assuming that the defendant is innocent, is as extreme or more extreme than the significance or alpha level, that tipping point that we've talked about, then we can reject the null hypothesis and conclude the alternative is likely true, that the person is guilty. This happens when the p-value is less than the alpha level. And I'll go ahead and say this now before we do anything, before we even start working through these problems fully. In your conclusion, in your wrap-up to every one of these problems, when you get to your explanation of what's going on, you need to relate your p-value to your alpha level. Since my p-value is less than my alpha level, then blank. Since my p-value is greater than my alpha level, then blank. That relationship between them is going to drive your decision of whether or not you reject the null or not, whether or not in our example the defendant is innocent or guilty. Okay, so if the p-value is less than the alpha level, that's when we say that we have data that is statistically significant at that alpha level. And when that happens, we can reject the null hypothesis and conclude that there is convincing evidence in favor of the alternate hypothesis or the alternative hypothesis. In other words, if the p-value is too low, which is going to be less than the alpha level, less than 5%, less than whatever that alpha level is set at, then the null hypothesis is rejected. And if you're a scientist, that's an exciting thing when you're doing research and you're starting to look at your results and you realize that you have statistical significance. That's when you get excited. Maybe you can publish it if that happens. So here's our example. Remember that golfer, Zach Holland, who kept up with all of his 7-iron distances and took data on that. Well, when he looked at his data from the sample that he took with the new 7-iron, and he performed a significance level at the 5% level, he calculated a p-value. Remember, that's a probability of 0.0224. How would we interpret this? If the null hypothesis is true and the standard deviation is 15, then we would see a result like what he got, as extreme as his sample, or more extreme than what we saw, occur 2.24% of the time, just by random chance alone. Okay, this doesn't seem like a very high probability. In fact, it's not. It's pretty low probability. We've been kind of talking over the past few chapters about this mythical 5%. Like once it's less than 5%, it's statistically significant. Well, this is less than 5%. So does this provide convincing evidence? Yes. Since the p-value is less than the alpha level, we would reject the null hypothesis and conclude that there is statistically significant evidence that the standard deviation length for all shots with the new 7-iron is less than 15. So he's got evidence here. Could he have made a mistake? Sure. But based on the procedures the procedure that he has used, he's got good evidence that the 7-iron is likely going to be more consistent. The new 7-iron is likely going to be more consistent. Well, that is it for today. So remember, you have got a few practice problems in your textbook and a little bit of reading to do to kind of make sure that this is all gelling with you. Remember, if you have any questions, feel free to text me through Remind, or you can see me in class the next time we meet.